Okay, we can start now. Today, we are very happy to have Ken Fogler here. He is a postdoc at UC Davis. He will talk about a new magnetic symmetry in d+2 dimensional QED.
Thank you very much for the introduction, as well as for the invitation to give this presentation. So I've been actually gone from Davis for like a month and a half now, so it really feels like I'm visiting Davis. Yeah. So as Dot said, so this is work on d+2 dimensional QED, and the main focus of this talk will be on this paper that came out this past July, and this was done with Mitra, who is currently a postdoc at the IAS. This paper is essentially a continuation of the story that Strominger introduced approximately 6 years ago when he discovered that there seems to be this equivalence between asymptotic symmetries and soft theorems. More generally, he discovered, in fact, that there is a triangle of equivalence between three seemingly different fields in theoretical physics. And this triangle of equivalence is now called an infrared triangle. So on the top corner, we have the soft theorems. These are theorems that are required for the consistency of the quantum field theory involved, and these are studied first in the context of gravity by Weinberg in 1965. On the bottom left corner, we have the asymptotic symmetries. The asymptotic symmetries were first studied by Bondi, Messner, Vandenberg, and Sachs in 1962, also in the context of gravity. And we will be focusing a lot more on the soft theorems and asymptotic symmetries side of the triangle for the remaining part of the talk. The final corner is a memory effect, and it's just as interesting. So this was first discovered by Zeldovich and Polnareff in 1974, and it's most easily understood in the context of gravity. So essentially what the memory effect says is that, suppose I have two stars that are orbiting around each other with fixed spatial separation. When I pass a gravitational wave between the two stars, I expect there to be a fluctuation between the distances separating the two stars. And after the gravitational wave has passed, the separation is now a fixed number again. However, the separation between the two stars before and after the gravitational wave's passing is different, and it is in this sense that the space-time retains a memory of the gravitational wave's passing. So as I already mentioned, I will be focusing on the side of the triangle that relates soft theorems to asymptotic symmetries, and I'll say a lot more about both of these later. And for the remainder of the talk, I will not talk about the memory effect. Let's just go through a little bit of history of the relevant papers that are required to understand what I will be talking about today. So in 2014, along with Mitra, Porphyriadis, and Strominger, we were able to show that the leading soft photon theorem in 4 dimensions is precisely equivalent to a word identity associated to certain asymptotic symmetries in QED. Now, one could wonder whether or not this equivalence between asymptotic symmetries and the soft theorem persists only at leading order, or whether or not there is a similar sort of equivalence that can be shown for the subleading soft photon theorem as well. And that was the focus of these two papers, one by Lysov, Pastersky, and Strominger, and one by Compiglia and Latta, where they show that indeed the subleading soft photon theorem can be understood as a word identity, at least in 4 dimensions. However, the case is a little bit different for the subleading soft photon theorem, because what they showed was that you can use the subleading soft photon theorem to derive the associated word identity, but you cannot go in the opposite direction. So whereas for the leading soft theorem, you have an equivalence between the asymptotic symmetries and the soft theorem, for the subleading case, the soft theorem implies asymptotic symmetry, but not vice versa. And finally, earlier last year, along with Mitra, we were able to show that all these results that people have studied in the past, which up until this point have only been done in even space-time dimensions, that all the results, in fact, also carry over to odd space-time dimensions as well. So this was very satisfying because it would have been very strange if this equivalence only existed in even dimensions. But the purpose of these two papers was to show that all of the results in this paper and these two papers, in fact, also is true in odd space-time dimensions. dimensions as well.
I have a question. For this leading soft photon theorem, this is applied to any loop order, right? Is exact, right?
For today's talk, we will restrict ourselves to tree level, but the leading soft photon theorem is tree level exact.
Tree level mean
It's true to all loop orders. Yes. So the goal of today's presentation is follows. So on the one side, we have the subleading soft photon theorem, which is a theorem in QFT that was first discovered by Lowe when he studied scattering processes. And on the other side, we have these asymptotic symmetries of QED, and these are large gauge transformations that leave the equations of motion invariant while changing the physical state. What we want to show in today's presentation is that we can derive a word identity associated to certain asymptotic symmetries of QED that is not only implied by the subleading soft photon theorem, but is in fact equivalent to the subleading soft photon theorem. And this is something that will be shown to be true in all dimensions. So essentially, whereas previously people have shown that the subleading soft photon, that this implies this, what we want to show today now is that, in fact, there is a word identity in which this implies a word identity, and the word identity implies a subleading soft photon.
Sorry, very naive question. Does this mean that if we live in space-time that isn't asymptotically flat, that the subleading photon theorem is wrong?
So in a space-time that is not asymptotically flat, we would probably have to take into account curvature effects. So everything I'm talking about today is in fact not just in asymptotically flat space-time, but in Minkowski space-times. So I think what would happen is that in that case, a subleading soft photon theorem, there might still exist. There probably would exist a subleading soft photon theorem still, but it might take a slightly different form. Does that make sense?
Probably. I mean, a typical space-time doesn't have any asymptotic symmetries at all.
Right. So these are asymptotic symmetries of the gauge field. So these would not be related to the space-time.
They probably require...
They do, yes, that's right.
Okay, then it's probably just a minor thing.
Maybe as I continue to go along, if the problem still persists, then you should ask me again.
Just to follow up on that question, what was the what role is played by the Minkowski metric as opposed to just the asymptotically flat part?
Right. So the Minkowski metric was required because we needed a scri plus and a scri minus. And essentially the entire analysis is built upon doing the proper expansion of the gauge fields near scri plus and scri minus. So it depends very sensitively on the boundary fallout conditions of the gauge fields near those two boundaries. So if you have something that's a little bit different, you can imagine that this would lead to non-trivial changes in the analysis.
Okay.
Did you have a question?
No, I'm just trying to say the asymptotic symmetry group for QD is I think I asked you before, is semi-classic symmetry or is the exact symmetry of this asymptotic symmetry?
So these would in fact they are exact symmetries of the theory.
Okay.
But they are symmetries of the so your question, yeah, so there's a little bit complicated. I think there's two questions in your question. One is what are asymptotic symmetries in general? And the other question is what are the asymptotic symmetries I will be talking about in QED? So asymptotic symmetries in general can be much more involved than what I will be presenting today. And what I will be presenting today, the asymptotic symmetries of QED, these are, in some sense, you can think of them as being exact symmetries of the theory. But as I will show in the last part of the talk, these symmetries have various that are associated to this. It's not exactly clear what their physical interpretation is, and in fact, that's something that I would love to understand better.
Okay.
All right. So to reach that goal, this is what we will. This is the roadmap for today. So we begin with a lightning review of the soft photon theorem as well as the concept of asymptotic symmetries. We will then construct what we will call the matching condition, and the matching condition will give rise to the conserved charge in the theory. We will demonstrate that the word identity associated to this conserved charge is precisely equivalent to the subleading soft theorem in d+2 dimensions. And finally, we will demonstrate that the charge constructed is associated to what we will call both electric and magnetic large gauge symmetries, and this is going to probably address your point. Okay, so that was where we're heading. Are there any more questions? Okay, so let's begin. So you are probably all familiar with this, but the leading soft photon theorem is precisely the theorem that relates the matrix elements of a Feynman diagram with an external soft photon insertion to the same diagram without an external soft photon. A picture is worth 1,000 words. So here I've just taken a figure from Weinberg Volume 1, where he shows the leading soft photon theorem. So here we have a scattering process. Alpha labels the incoming particles, beta labels the outgoing particles. This blob in the middle is just some complicated interaction that takes place. And this wavy line is a photon with momentum q. As we take the momentum q to go to 0, this is what we mean when we say that we're taking the photon to be soft. And the leading soft photon theorem, what it wants to relate is exactly the Feynman diagram with this soft photon attached to the same Feynman diagram without the soft photon. Now, when deriving the leading soft photon theorem, there are two ways I can attach this soft photon. I can attach it to one of the outgoing lines, or I can attach it to one of these incoming lines.
Can I attach it in the loop?
Yes, good. So you may wonder why I cannot attach it to one of these internal lines, but I will explain in the next slide why we do not need to consider such diagrams when deriving the leading soft photon theorem. So in equation form, this is what the leading soft photon theorem says. So on the left-hand side, I have the n+1 particle Feynman diagram. The photon has momentum p gamma with polarization epsilon, and we're taking it to be soft, so p gamma is going to 0. On the right-hand side, notice that it takes a very simple form. This is, in fact, just a C number. Eta is +1 for outgoing particles and -1 for incoming particles. These are the various external momenta. This is the electric charge of the various particles, the E times Qi. And this is simply the original n-particle Feynman diagram. Now, there are two things I want to comment about this equation. The first thing to note is that this factor, what we call the leading soft factor, that it is proportional to 1 over p gamma. So in the limit that we take p gamma going to 0, this term in fact diverges, and this is what we call a Weinberg pole. So this is why we do not need to consider those diagrams that involve the soft photon attached to one of the internal lines, because those diagrams contribute terms that are at most order 1 and are hence subdominated by this Weinberg pole that is order 1 over p gamma. The second thing I want to remark is that notice that this term, this leading soft factor, is in fact very simple. It only depends on the various external momenta and the electric charges. And the fact that it is so simple suggests that perhaps there is some sort of universality to the fact that it's so simple, that it is so universal, suggests that perhaps it may arise from some symmetry in this theory.
What is eta I?
Eta I is +1 if the particle is outgoing and -1 if the particle is incoming.
Okay.
So it's just telling you.
You're saying that when I'm attaching photon in the loop or something like that, I don't have this.
Those
pole.
terms will be order 1. Yes. That's right. You can think of this is because the Weinberg pole appears when the line goes on shell, and for these internal lines,
You're now on shell.
they're not on shell. So, and this was indeed shown to be equivalent to the word identity associated to asymptotic symmetries of QED. So this was where that is related to the leading soft photon theorem. Now you may wonder, there is a leading soft factor, it's order 1 over q, but can we say anything about the order 1 piece, the subleading piece? And the subleading soft theorem precisely addresses this question, and it was discovered by Lowe in the 1950s. And there he showed that indeed the subleading soft photon theorem also has a lot of very nice properties. And more recently, it was shown that this term is also universal for all minimally coupled theories by these authors. Therefore, what we will call the soft photon theorem, which includes both the leading and subleading piece, at tree level, we can write it in this form. So the first factor is the one that we flashed. So this is the leading term. This is the order 1 over p gamma, the Weinberg pole. And S1 here is what we call the subleading soft factor. And notice that it is order 1 because p gamma appears in both the numerator and the denominator. The JAB is the angular momentum tensor. And for the purposes of today's talk, for the rest of it, we already understand exactly how to write the leading soft factor, how the leading soft theorem is related to word identities, and now we are going to focus on the subleading soft factor and show that it is also equivalent to certain asymptotic symmetries in the theory.
The subleading term also don't receive contribution from photon attached.
The subleading term will receive contributions from those.
Is it included here in this expression?
It is, at least to tree level.
You're going to explain what the indices A and B, what they act on? What are those?
Oh, A and B are those standard Minkowski indices. So it just goes from 0 to
Those are just, okay.
Yeah.
And then J is the angular momentum of which? Of what?
of the various external particles. So J includes both their angular momentum and their spin.
Of each one?
Of each
I
one,
see,
yes.
okay.
So little I indicates which particle.
So
it
A
is.
and B are just, they run from 0 to D minus 1.
To, in this case, D+1.
A D plus.
Yes, yes. But
Okay.
Exactly.
Got it.
But how do I see that the photon attached to the internal loop included here?
Photons attached to internal loops will not be included because we are working at tree level here.
I see.
Yeah. Okay, now let's move on to asymptotic symmetries. So symmetries are one of the most useful tools that we have in theoretical physics. And one way to think of these certain symmetries is in terms of a word identity, in the sense that these are simply that the charges that generate these symmetries commute with the S matrix. We then will simply define the asymptotic symmetries to be symmetries that act on the physical states in a non-trivial manner. So it's a very general definition. In many cases, these asymptotic symmetries are local in space-time coordinates. And because of that, we will oftentimes also call these asymptotic symmetries large gauge symmetries. Because as we learned in school, gauge symmetries are symmetry transformations that are parameterized by a function that depends on space-time coordinates. But the ones we learn in school, they are always parameterized by a function that dies off at asymptotic infinity. And hence, these are merely gauge redundancies. They are not true symmetries of the theory because these gauge symmetries have no chance of acting on the asymptotic physical states. The asymptotic symmetries we are talking about, they are large in the sense that they can act on, these are parameterized by functions of space-time coordinates that do not die off at asymptotic infinity, and therefore stand a chance of acting on the actual physical states, the asymptotic states. So the redundant gauge symmetries we will oftentimes call the trivial gauge symmetries, and the ones that are actual physical symmetries are the large gauge symmetries.
How does it relate with this instanton?
What instanton?
No, I'm just curious because in instanton also has some large gauge transformation and infinity, right?
Are you thinking of, okay, so are you thinking of these topologically?
Yeah, topologically.
Yeah, so these are not really.
Totally different.
Yes, yeah, I have a remark about that.
Okay.
But yes, that's oftentimes the nomenclature causes confusion because large gauge symmetry is an overloaded term.
Yeah.
Yes. Apologies, but I didn't come up with this terminology. In any case, in fact, this is common. So this definition of large gauge symmetries allows for topologically trivial symmetries as well. So these large gauge symmetries can be connected to the identity. Now, for the time being, we want to take a very operational standpoint because we don't understand completely, or we don't even understand very well what these large gauge symmetries are at the moment. So our operational standpoint is large gauge symmetries are physical if only if it gives rise to a non-trivial word identity. So, I mean, this is almost in some sense by construction, but this is the standpoint that we will adopt. Now, we don't know currently whether or not all large gauge symmetries or asymptotic symmetries are physical, but we definitely know that at least some of them are. And this is the whole point in this strong link that was established between asymptotic symmetries and soft theorems. Because soft theorems are simply the word identities for asymptotic symmetries, and soft theorems are certainly not trivial. So just a few examples. The one I already explained was the leading soft photon theorem. This was shown to be equivalent to the word identity associated to certain asymptotic symmetries in QED in 4 dimensions. And this has been extended since 2014 to both massive QED as well as to all higher dimensions greater than 4. And similarly, we have an analogous story for the gravity case, where the leading soft graviton theorem is precisely the word identity for supertranslations in 4 dimensions. Supertranslations being the generators of the asymptotic symmetry group of asymptotically flat spacetimes. And this equivalence is remarkable because, at least from my viewpoint, since soft theorems were first studied in QED in 1937 by Bloch and Nordsey, later by Lowe and Company in 1958, and finally expanded by Weinberg to gravity in 1965. And this was work that was done by particle physicists. Asymptotic symmetries, on the other hand, first appeared in the work of BMS in 1962, where they deduced the symmetry group for asymptotically flat spacetime. And this was work that was done by general relativists. And the tools that these communities used were quite different. One was using perturbative Feynman diagrams to study the soft theorems. And the other group was using the asymptotic structures at no infinity to study the asymptotic symmetries. And each community, for over half a century, wrote thousands of papers on their respective subjects. And now, we are starting to understand that there are in fact 2 sides of the same coin. Of course, this equivalence, so far, has only persisted for the leading soft theorem level. And the goal for today's talk, as I already mentioned, is to extend this equivalence to the subleading case as well. So now let's get down to showing, defining what is a proper word identity to consider. So the coordinates that we will do our calculations in, it's called flat null coordinates, and we will be working in d+2 dimensions. To illustrate that, I've taken this figure from one of Strominger's earlier papers. So in this paper, he drew a Penrose diagram for 4 dimensions. For us, we will be working in d+2 dimensions, but it's actually quite simple to use this diagram for d+2 dimensions. The only difference is that whereas here, each circle represents a conformal 2-sphere, the asymptotic 2-sphere at infinity, the celestial 2-sphere. For our case, we will be this circle will represent a d-sphere, the celestial d-sphere at asymptotic infinity. R is the radial coordinate, so taking r going to infinity takes us to scribe plus, and u then parameterizes the direction along scribe plus. So u going to infinity takes us to scribe plus plus, and u going to minus infinity takes me to scribe plus minus. The funny thing about this flat null coordinates is whereas r, usually the radial coordinate goes from 0 to infinity, for us, it will in fact go from minus infinity to infinity. And taking r going to minus infinity will land me on the antipodal point of the celestial d-sphere on scribe minus. U then will then parameterize the direction along scribe minus, so u going to plus infinity takes me to scribe minus plus, and u going to minus infinity takes me to scribe minus minus.
I understand it. What's
Yes.
What's u?
U is, think of it as no time, if you want.
No time.
Morally speaking, yes. So it just parameterizes the null direction
R is
along
just
scribe plus or scribe minus.
R is just radius.
Pardon?
R is just radius.
R is, in some sense, the radial coordinate, yes, but it goes from minus infinity to infinity, so that's the point I wanted to be clear about.
Okay, and
Yes.
the Z is just the complex angle.
Yes, so here it's marked with z. Z is a complex angle. For us, because we're working in d+2 dimensions, we will have like complex number. We will have like,
D angle.
yeah, we'll have d angles, yes. Okay, so we will be analyzing the fields near scri plus and scri minus, and this is where the massless fields live. And so for simplicity, we will only focus on massless particles in our theory.
You mean for the electron also massless? Sorry.
Yes, we're assuming the electrons also massless. This is, yes. Think of this as a toy model for standard QED. We have an idea for how to extend it to massive case. It doesn't tell you anything conceptually new. It's just makes it complicated. Some complication in the calculations. But the extension from massless, these massless cases to massive cases have been done by several authors, which I can give you references if you want. Not for this case, but for like 4-dimensional QED. Okay, so just to give you guys a little bit more intuition, the d+2 dimensional flat null coordinates is given just by this expression. So here's the standard Minkowski coordinates, and in flat null coordinates, it's just minus du dr plus r squared delta ad dxa dxb, where little a and little b are essentially running from 1 to d. So these are the polar coordinates of our theory. And in fact, it is because the metric looks so simple that we are able to simplify a lot of our calculations, which is always helpful. Okay, so the equation of motion in our theory, it's just QED, so it's just Maxwell's equation. So J is the matter current, and F is simply the Abelian field strength. And as we all learned in school, there's a local symmetry under which we can take the gauge field A mu going to A mu plus del mu epsilon, and the equation of the motion remain invariant under this local symmetry. When we learned about this in school, we always took epsilon to vanish at asymptotic infinity. So this would, in that case, be a trivial gauge symmetry. But for us, we can take epsilon to be non-trivial on the d-dimensional celestial sphere. And in that case, it will become a true asymptotic symmetry. Nevertheless, we can still use the trivial gauge symmetries to gauge fix. And the gauge condition that we will choose is we want to set the u component of the gauge field A to be 0. To solve Maxwell's equations, we can now do a decomposition of the general solution into two pieces, the radiated piece and the Coulombic piece. The radiated piece is simply the solution to the homogeneous Maxwell solutions. So this is simply the wave solutions that that are in our theory. And the Coulombic piece will be the inhomogeneous solution to Maxwell's equations. So this will be the part of the gauge field that is sourced by the matter current. Now, because I'm interested in the gauge field near scri plus and scri minus, which is when R, the magnitude of R, becomes very large, I want to do a large R expansion of the Coulombic field strength. And the way that we determine these fall-off conditions is using Gauss's law. So, for instance, FUR, this is simply the radioelectric field. So we know from Gauss's law that the integral of the radioelectric field over the d-dimensional sphere surrounding it gives us the charge inside the sphere. So we know when we do the integral, we want the charge to be non-zero but finite. So the integral over the metric contributes a factor of r to the d, which means that we want the radioelectric field to fall off as 1 over r to the d in order to ensure that the charge is finite but non-zero. Once we have the fall-off conditions for FUR, we can then use simply Maxwell's equation to determine what the fall-off conditions for the rest of the field strength components are. And similarly, we can also determine the fall-off conditions for the matter current. Now, the details of these fall-off conditions is not important at all. The only thing I wanted you to take away from this slide is that it allows us to solve Maxwell's equation order by order. And we will use the fact that we can solve Maxwell's equation order by order in the remainder of the analysis.
Oh, that means expansion parameter is 1 over r. That's
the expansion parameter is 1 over r, exactly. Oh, and I just wanted to mention one more thing. Throughout my talk, oftentimes I'll have some field, and then the coefficient will be some number. And all I mean by that is it is the coefficient of the field, the 1 over r to that number. So for instance, here I have ju to the d plus n. That simply means this is the coefficient of the 1 over r to the d plus n component of ju. And I'll remind you whenever that appears.
Let me remember something. Is this I minus because r go to minus infinity, I plus is r go to plus infinity?
Oh, very good. Sorry.
The definition?
Sorry. Yes, exactly. Exactly.
Oh, it's r, okay.
Yes. So r goes to plus infinity is on square plus, r going to minus infinity is on square minus.
Okay. Which means that at this boundary you still have time.
Pardon?
I mean, time is on the boundary is also minus infinity. Sometimes it,
Time?
yeah. Near this the symptonic, let's see, I plus minus, you still have time, right?
Near to, I mean, square plus and square minus, there is still time, but the time is, the t coordinate is related to these in a, slightly more complicated fashion. The flat null coordinates that we chose, it makes the structure near square plus and square minus in terms of these r and u's very simple.
Okay.
But if you want to think of it using the traditional coordinates like t,
Yeah.
little t, and the standard radial coordinate, it's very complicated.
Okay. It's not,
So it's not, yeah, so I'm happy to discuss with you after this,
Okay.
but it might derail the
Sure.
rest of the presentation. Yeah. Okay, now we come to perhaps one of the most important slides in this presentation, because ultimately we want to study scattering processes. And scattering processes relate quantities in the far past with quantities in the far future. And in particular, for us, what we want to do is we want to relate the field strength near square plus, which is in the far future, with that near square minus, which is in the far past. And of course, scattering preserves Lorentz invariance, and so this is something that we want to preserve. Now, this is the proposed matching condition that was originally put forth in the 2014 paper when we were studying how to relate the leading soft photon theorem to the asymptotic symmetries. So this is, so I'll just break this down. So as you can see, what we are doing is we are matching the 1 over r to the d component of FUR as square plus minus, which is on the sphere over here, with the minus of the field, the radioelectric field, FUR on square minus plus, which is over here. So we are matching the radioelectric field in the on the sphere here with the radioelectric field on the sphere here. So it's matching across spatial infinity. Now, the first thing you might be worried about is this minus sign, but this minus sign is just an artifact of us using these flat null coordinates where r goes from minus infinity to infinity. Now, if we had picked coordinates where r goes from 0 to infinity, we would never get that minus sign. Also, the other thing, whenever you're reading this literature, is that this is often called the antipodal matching condition, because essentially, remember that as r goes from infinity to minus infinity, we then go from one point on the d-dimensional celestial sphere to the antipodal point of the d-dimensional celestial sphere. So this is actually relating quantities at the antipodal points. And to intuitively understand this, imagine if I have a particle coming in the far past from the south pole and leaving in the far future at the north pole. If I do a Lorentz boost of the particle in the far past in the south pole, I would expect a corresponding boost of the particle in the north pole, the antipodal point in the far future. And this is how you should think about this antipodal matching condition. When we first proposed this was a guess, and this guess was motivated by the fact that if we take the linear weaker potential, we take r going to infinity first, and then take u going to minus infinity, which will land us on square plus minus. And we compared it with the limit where if we had taken r going to minus infinity first, and then u going to infinity, which will land us on this point, we would have gotten exactly this matching condition. Now, this matching condition, since we conjectured in 2014, has been put on much more solid footing. It has been proven to be true under relatively mild assumptions. The reason why this matching condition is so important is because it immediately implies a conservation law. Because we can just simply take the matching equation, multiply both sides by some function epsilon, and do the integral over the celestial sphere. And the result is this classical conservation law, which is that q epsilon plus is equal to q epsilon minus.
So am I supposed to think of that law as a quantum operator equation?
You mean over here?
No, sorry, I should have asked it before. The previous, the boundary, the matching condition there,
Yes.
this funny matching condition.
Right.
Is that how I should think of it?
Yes, eventually what we're going to do is we're going to put this into an S matrix element. And so
It's supposed to hold inside,
an S matrix.
inside,
It's-
it's a sandwich between asymptotic
Exactly.
states for an S matrix.
Precisely. Yeah, so that's exactly the way to think about it. Yeah. But so far, at the level of classical, at the classical level, this is what we have. Now, the way I've written it so far, this Q is just some quantity, and we don't know what it is. But as it turns out, and was verified, this Q epsilon as written precisely generates the large gauge transformations in QED, parameterized by the function epsilon. And as a sanity check, notice that when epsilon is equal to 1, then FUR here, this is simply the radioelectric field. So we are simply doing the integral of the radioelectric field over the celestial sphere. And this gives us precisely the usual QED charge that you're familiar with. Okay, so now let's move on to the subleading matching conditions. Originally, people guessed that, okay, the leading match, to get the leading soft theorem, we matched the 1 over r to the d component of the radioelectric field. Maybe to get the subleading soft theorem, what we should be doing is matching the 1 over r to the d+1 component of the radioelectric field. And that was a very natural guess. So here, I have written the 1 over r to the d+1 component of the FUR, the radioelectric field, using Maxwell's equation in this form. The first thing you would notice is that there is a term that is linear in U. So if we want to do this standard matching condition, we're matching it on scribe plus minus to that on scribe minus plus. So those are points on the Penrose diagram where U is going to plus or minus infinity. And so this term would diverge. So that is a problem. However, we can choose instead just to project out the divergence and simply match the finite piece. And this 1 minus U del U achieves precisely that. So the original guess that people had about the, deriving the subleading soft photon theorem from a word identity is simply to match the subleading component of the radioelectric field. And in particular, and then they, at least they project out after projecting out the divergent piece. And so the matching condition that was guessed was originally this. Once we guess that, we can then just do the same song and dance. We simply multiply both sides by some function epsilon, integrate it over this d-dimensional celestial sphere. That gives us a quantity. We show that it's some charge in the theory, and then we write down the corresponding word identity. So as I mentioned, the matching condition implies a word identity that is associated with the subleading soft photon theorem. However, they are not equivalent. The word identity that one writes down by assuming the matching condition I had in the previous slide, it is in fact the divergence of the subleading soft photon theorem. So whereas the subleading soft photon theorem implies a word identity, the opposite implication is not true. And that should not be too surprising, because the above matching condition I wrote down, we are matching one component of the field strength, in particular the radioelectric field. On the other hand, there are d-independent subleading soft theorems, one for each polarization of the soft photon. Now this problem does not occur for the leading soft theorem, because in the leading soft theorem, there's actually a constraint that relates inserting a soft photon into an S matrix element with different polarizations. So in the leading soft theorem case, there is in fact only one independent leading soft theorem. This constraint does not exist at the subleading level, so there are d-independent theorems. And we can certainly not expect to get d-independent equations from one matching condition. At the very least, we need d-matching conditions to derive this. So we need to guess what are perhaps the proper matching conditions to write down, or in fact the d-matching conditions. So to do that, we go back to Maxwell's equations, where we are able to solve it order by order. And this is what Maxwell's equation tells us for the 1 over r to the d+1 component of FUR. Now, if we are going near scribe plus minus or scribe minus plus, we don't care about the matter current, because that will just vanish. But notice that this is precisely equal to the divergence of the 1 over r to the d component of the FRA component of the field strength. So this strongly suggests that perhaps the proper matching condition is not matching FUR, because when we matched FUR, we got the divergence of the subleading soft theorem. But if we match FRA instead, and little a goes from 1 to d, so this is in fact d matching conditions, then what we will get is a word identity that is equivalent to the subleading soft theorem.
Why did flux GR go to 0 at infinity?
Pardon?
Why you neglected the GR?
JR?
Yeah.
Because near spatial infinity, there's no matter.
There's no flux in.
Yes.
So FRA has the same divergence in U as,
FRA has the same divergence as one can show. Yes, that's right. So this is going to be our conjecture matching condition, and we will now show that this matching condition is precisely equivalent to the subleading soft theorem. Okay, so once we have the matching condition, we can now go through the same song and dance. Except now we have a Lorentz index, so what we need to do is contract it with some vector field on the celestial sphere. We integrate over the celestial sphere, and we get the classical conservation equation Qy plus is equal to Qy minus. Now, so far I haven't told you what Qy is, but we must check what it actually does when you act on the asymptotic states in the theory. And we will later show that this is a charge that is associated to what we call divergent electric and magnetic large gauge transformations. And I will mention, and I will talk about what I mean by those words near the end. And what we want to show now is that the corresponding word identity is precisely the subleading soft theorem. So let's get started. The first thing we want to do is decompose this charge into two pieces, what we call the soft piece and the hard piece. The soft piece only involves the radiative components of the gauge field. And the reason we call this a soft piece is because, as we will show after our analysis is done, inserting the soft charge into the S matrix element essentially creates a soft particle that is associated to the subleading soft photon. And this hard piece is precisely the part that is corresponding to the Coulombic piece of the gauge field. Now, the form of the soft charge is actually dimension dependent. So it depends on whether or not we are sitting in even dimensions or odd dimensions. So we have to do the analysis separately, depending on our dimensions of our space-time.
What do you mean by soft and hard?
Right. So the soft, so these are just names. The soft piece, we call it the soft, is because this will be related. So this is currently an operator, right? So when we insert this into S matrix element, and I will show in the next couple of slides that this will correspond to inserting a soft photon. Yeah. And the hard piece is we call it hardest because this will act on all the other hard particles in the scattering amplitude.
Because it's the Coulomb part, right?
This is a Coulomb. Yes, exactly. All right, so let's begin by looking at the soft charge. So we want to determine what the soft charge is, and the first thing we want to do is do a field expansion in large R near scri plus or scri minus. This is just a usual Fourier decomposition of the gauge field, which we can do because this is simply the plane wave solutions to Maxwell's equations. And simply, this is just written in these funny flat null coordinates. So here, O plus is just a annihilation operator near scri plus. O minus is an annihilation operator near scri minus. And similarly, O dagger plus and O dagger minus are the corresponding creation operators. The little a here, you can think of this as a polarization of the soft particle that we are inserting. And the reason it looks this, in this sort of funny form when we do this Fourier decomposition is just the nature of the coordinate system that we chose to adopt. The details of that is not important. What I do want to stress is that here we want to make an assumption. We want to assume that because we are interested in what happens when we take the energy to go to 0, we want to see, we want to do a Laurent series in these creation and annihilation operators. So notice that when we take n going to 0, this is just a 1 over omega piece. So the OA0, what that will do is it's essentially inserting a soft photon, and then we are extracting out the Weinberg pole piece. So This is why we will call OA0 the leading soft photon operator. But that's not the one we're concerned with, because we're concerned with the order 1 piece. And the order 1 piece corresponds to n is equal to 1. So inserting an OA1 in here will then give us precisely the it corresponds precisely to inserting a soft photon and extracting out the order 1 piece. So that will be the subleading soft photon piece. So we will call OA1 the subleading soft photon operator. So now we have to go to different dimensions. So first let's look at even dimensions. Now we want to do, in even dimensions and in odd dimensions, we were able to work out the complete large R expansion of the gauge field. The details of this is not important. The only thing I want to stress in this slide is that we want to work out what the integrand of FRA to the D, what the 1 over R to the D coefficient of FRA is. So all we need to do is simply isolate the components of the gauge field that gives us precisely the coefficient of 1 over R to the D in FRA. Because this is the integrand of the charge that we are calculating. And so the only thing I want that you should take away is that we are able to write this explicitly in these closed form expressions. And similarly, in odd dimensions, we can do exactly the same summing gates. It's slightly different, but at the end of the day, we are able to write down the integrand for the charge. And notice in all these cases, the integrand involves OB1. So these are the operators that correspond to inserting a soft photon and then extracting out the subleading soft term. Just to mention a caveat that I swept under the rug in this derivation. So actually in even dimensions, it turns out that when you look at the charge actually has log divergences. And therefore, in order to ensure that the charge is well defined, we needed to make this funny assumption. So the assumption is that we want the strict zero energy limit of these creation operators to be exactly the zero energy limit of the annihilation operators. Now, before you think this assumption is completely crazy, I just want to remind you that these zero modes of creation and annihilation operators, is very different from these finite energy in creation and annihilation operators. Because when I hand you a finite energy creation or annihilation operator, what's going on is that I am sitting on top of a particular vacuum, and I am generating finite energy excitations on top of this vacuum, thereby creating a Fock space. These strictly zero energy creation and annihilation operators, what they are doing is they are taking us from one vacuum to a completely different vacuum with some different number of soft particles in the vacuum. So they are in fact, perhaps the proper way to think of these is a vacuum shift operator instead of some limit of creation and annihilation operators. So just to emphasize, we are, this assumption amounts to that the strict zero energy limit of both creation and annihilation operators just produces a new vacuum state. Now, it would be fantastic if we can understand where this assumption comes from, but in order to ensure that the chart is well defined, we do make this assumption for the remainder of this talk.
So maybe it's not related, but I have the impression that we have the boson boson. At that part, the one of the conditions you have boson boson is that there is a equivalent of all the let's say equivalent of all the vacuum. One boson boson, two boson boson, three boson boson.
Sure.
Because then you have a massively bound state. And you have a massively particle because one particle state and two particles same. This is the same thing?
Yes, so you can think of the soft particles as boson bosons.
Okay.
Subject to these asymptotic symmetries.
Okay.
Yes. Okay, so that caveat aside, we are now able to write down the soft charge in terms of these subleading soft photon operators, these OB1s. And you don't need to worry about the explicit form of this, it's just telling you that we can now write down the soft charge in terms of these soft photon operators. Okay, that's all I want to say about the soft charge. Now, we can similarly also work out what the hard charge is. So using Maxwell's equations, we can write down the hard charge in terms of these matter currents, and then we can simply determine how these matter currents act on the asymptotic states in the theory. And after a bit of algebra, one can show that the hard charge acts on these asymptotic states in this following form. So now we have the word identity, and it's clear how we should proceed, because the word identity tells us that to go from the classical to the semi-classical picture, what we want to do is we want the classical conservation law sandwiched inside an S matrix element, and we impose that that is equal to 0. So this is the word identity that we will work with. And notice that we can decompose the charge into a soft piece and a hard piece. We can then just move all the hard pieces to one side, keep the soft pieces on the other side, and the result is the following. And what we have done is we had the hard charge act on all the asymptotic states in the theory. And this is the form. So on the right-hand side, notice that we have some complicated expression. It's a differential operator. It's acting on the original scattered matrix element. On the left-hand side, we have the soft charge. But the soft charge is related to a subleading soft photon operator. And so this is starting to look very similar to the subleading soft theorem. And in fact, our claim is now that this is a subleading soft theorem in null flat coordinates in disguise. So now what we need to do is basically make sure all the factors of i's and pi's and 2's are all correct. So just to remind everyone, in standard momentum coordinates, the subleading soft photon theorem tells us the following. So this order 1 over e gamma, this is a leading soft theorem. We don't care about that. And this is a subleading soft theorem. So we are isolating this particular term in the expression.
Right. From this formula,
Yes.
how can I see that you have a D independent subleading soft theorem?
Oh, little a. Little a runs from 1 to d.
Sure. Okay. From leading part, that's a sum. From leading,
Sorry?
from leading part, they also depend on A, right?
Little leading part also depends on a, but there is a constraint equation that you can derive in the leading soft theorem that shows that all the little a's, essentially that all of them are related.
Okay.
I can tell you more about that.
This subleading soft theorem is true only at tree level?
This is true only at tree level. Yes.
And so, these other manipulations, how do they know that it's only at tree level?
Right. So we do expect that at loop level, then what we need to do is include extra correction terms that are.
But do you understand from the other point of view where tree level is essential, at what step?
Yes. The suspicion is that at loop level, it's possible that either the matching condition needs to be modified, or let's see. Yeah, I guess in this analysis, probably what's going to happen is that the matching condition needs to be modified. That perhaps this matching condition is true only at tree level. Yeah. The status actually of this equivalent between asymptotic symmetry and soft theorems for loop corrections, in fact, there's still a lot of work that's trying to be done, because there the story is a lot less clear, because precisely for some of the, one of the things that you're raising, the issues is that it's not sure, like, what should be changed to account for these loop corrections. There's been limited work that is done on this, but
one of the things that just strikes me, I'm not really familiar with this, is that normally when we talk about the S matrix, we don't talk about the whole null, the scribe plus, scribe minus, where you are at scribe plus, scribe minus, because we just have an S matrix that's a function of initial and final momentum. So somehow, in what you're doing here, it looks like you're introducing some additional structure that's not in the way, at least, I'm used to thinking about the S matrix, right? Because like I said, you just have initial position and final momentum. So to me, I just wonder, to me looks really interesting, and so I just wonder, it seems like what one needs is something like a somewhat fancy or a different, modified sort of formulation of the S matrix where you understand how to talk about scribe plus and scribe minus in a legitimate quantum mechanical way. Have people tried to think about that, or is that known how to do that?
I don't think so. There has, I mean, one of the things that I know that people often talk about wanting to do is trying to connect this sort of like analysis to what people in SCET, what they do. It's not entirely clear to me whether or not that will address the concerns that you have. But the reason why people want to do that connection is because at least a lot of the people in the SCET community, they seem to think a lot of the equations that we have are very similar to things that they have studied, but except that there is some sort of difference in language, and one would like to make this sort of this understanding of the S matrix, like the way we think about the S matrix, into like the way sort of people typically think about S matrix elements. But it seems I haven't followed that story too much, but it's at least when I talk to people, I mean, people have wanted to make this connection for like 5 years now, and there just seems to be a lot of very striking similarities. But whenever people try to make it like pin down something precise, it seems to like problems arise. And so this probably is just telling us that there's still a lot that we don't understand. But I do think that there's probably some sort of connection that is precisely what you would like to see. I just don't know. Perhaps people are working on it, but I'm not familiar with any results so far.
I think there is a standard parameterization of momentum in terms of coordinates on the scribe, right? Because all you need is to know the momentum determines a direction, which determines a point on the celestial sphere.
In 4D, this is just spinor analysis.
Yeah.
The spinor variables, if you normalize them the right way, they're just z and z bar on scribe.
But so if I have a final floor momentum, where does it point on scribe?
So if it's a null momentum, then
You're saying it's just, I can think of it as just a Fourier transform on its side. So then it's just the usual, right?
But presumably that's true only in 4 dimensions, right? It will not-
in 4D, I know how to formulate that.
Yeah. But I guess in higher dimensions, this would be something that would be used.
But there seem to be more fundamental obstructions, conceptual obstructions to thinking about this beyond tree level. Just related to the fact that the S matrix is not especially meaningful for massless particles. You have to deal with dressings, you have to talk about.
Yes, that's right.
And so the S matrix is some pre-observable that we know how to talk about very robustly in momentum space with inner regularization scheme, but we don't really have it's not the right kind of observable.
That's right. Yeah, one of the things, in fact, that what we are currently trying to understand is precisely how to study these things in terms of dressed states. So that perhaps the conventional Fock space, the reason we are getting these infrared divergences is simply that these are not the states that we like. Essentially, one of the things that these asymptotic symmetry and soft theorems equivalence tells us is that oftentimes, every time we have a scattering process, it takes us from one particular vacuum state to a different vacuum state, where there's a lot of new soft particles in that new vacuum. And if you try to force yourself to stay in the same vacuum state after scattering, then this conservation law is violated, and hence we get these infrared divergences. So one thing that would be very, very nice to work out is to see if there is a formulation of the S matrix program where we just simply don't see infrared divergences from the onset. And that's something that is work in progress. Just to continue, to remind everyone, this originally we had the subleading soft photon theorem in momentum coordinates. We can then translate it into flat null coordinates, and it takes this form, where IAB is the tensor defined there. And the argument that we want to give now is that this equation is precisely equal to the word identity that I flashed a few slides ago. So let's just begin. So first, let's show that the soft theorem that I just wrote down implies the word identity. Now, depending on whether I'm in even dimensions or in odd dimensions, I will act on the soft theorem using a slightly different operator. But in either case, we recover the word identity, depending on if it's in even dimensions, I get the even dimensional word identity. If it's in odd dimensions, I get the odd dimensional word identity. So far, I have not done really anything new because we already know that there's a word identity that is implied by the subleading soft theorem, and there's no surprises there. What is interesting is that the word identity I wrote down, in fact, also implies a soft theorem as well. So recall that the word identity I wrote down is written in this form, where YA is some arbitrary vector field. I can choose YA to be this IAB delta BC vector field, and if I choose this particular choice of YA and I substitute it in, after some algebra, I get precisely the subleading soft photon theorem. So this completes the demonstration that the word identity we wrote down associated to the matching condition is precisely equivalent to the subleading soft photon theorem.
Is that the basis of the YAs?
Oh, yes, you can think of, well, YAs is, it's like all possible vector fields that you can put on. In some sense, you can think of the particular choice I wrote down as a set of bases. Exactly. Okay, so in the final, minus 1 minute, I just want to quickly explain what are these charges, because I feel you would be unhappy if I didn't at least say a few words about that. So the charges that we studied, if you may recall, is written in terms of the FRA components of the field strength. Now, what we want to do is we want to do a Hodge decomposition on the vector field y, where we write it as the gradient of a scalar function plus the derivative of a two-form field. Now, after doing that and using Maxwell's equations, I am able to recast the charge in the following nice form. Now, the first line, it should look a little bit familiar, because this is simply the original matching condition that was proposed by Campiglia and Latta, where they matched the subleading piece of the radioelectric field, the 1 over r to the d+1 component. This is called the This is a so-called the charge that is associated to the divergent electric large gauge symmetries. It is electric because this is associated to the radioelectric field, and it is divergent is because these are essentially the sort of the these are the large gauge transformations where the function is linear in R. So these are parameterized by divergent functions. The way to see this is because if I integrate over FUR, there's a 1 over r to the d+1 term that comes from here. There's an r to the d term that comes from the metric. So that means that lambda secretly has a piece that is linear in R. However, after doing this integral, actually all the r's cancel out, and what we are left with is a finite large gauge symmetries, but is associated to these asymptotic symmetries that are parameterized by these divergent functions. Now the second line this is the new charge that is associated to that we have discovered, and these are the new magnetic symmetries. These are the divergent magnetic large gauge symmetries because they correspond to FAB, where these are the magnetic fields in the theory. So this is something that's very interesting because even though we don't have any magnetic monopoles in the theory, at the end of the day, it seems to have these asymptotic symmetries that correspond to these divergent magnetic large gauge symmetries. We currently don't have very much intuition for what these objects are, so it would be fantastic if we can understand these a little bit better.
What's a KED?
A KAB is just some two-form field. Yeah. Okay, let's just summarize what we have done. So we wanted to write down the charge in terms of FRA. So to do that, we performed an asymptotic expansion of RA in both even and odd dimensions. We then extracted the 1 over r to the d component of the field strength component and wrote down the corresponding soft and hard charges. After we have the charges, we can then use the matching condition to write down the word identity, and then we show that it is precisely the subleading soft theorem. And finally, we demonstrated that the charge associated to this matching condition is precisely these divergent electric and magnetic large gauge symmetries. So there's Okay, I'll leave that at that. Thank you very much.
Any question? Mark?
So, if I wanted to understand these large gauge symmetries as ordinary large gauge symmetries, what I would do is take the commutator of the charge with the potential and see how the potential changed under that commutator. What happens? I think with the leading, you just get a standard gauge transformation by partial mu epsilon.
Right.
So presumably for your electric part, you get some similar thing.
Yeah, so the electric part was what I think what you will get is you would, so in the leading case, you said you would get some, it would be what you typically expect, you expect however amount you want the large gauge the regular large gauge transformation parameterized by some function epsilon.
Yeah.
In the subleading case, I think what you will get is you will get, so if you just take the, so if you just write down the charge that corresponds to both the leading and the subleading piece, because you can think, because you can think of this piece, instead of integral over FUR to the d+1, you can just think about this as the entire integral of the FUR gauge field, right? So in that case, what you will get, if you put in the so the leading piece is what you expect. The subleading piece is what you will get a term that is where the function parameterizing the large gauge transform is linear in the radial coordinate.
Right.
Yes.
That's fine. It's
Yes.
the magnetic piece that I'm
Oh, I see.
about.
Oh, okay, yeah. So you're saying, wondering what the magnetic piece is?
Yeah, what's the commutator of the magnetic piece of that charge with the gauge potential?
Right.
It's tricky because
Yeah,
the
that's-
reason it's 0 or, well, no, I guess, well, the commutator with AA is 0. But the commutator with, and you've chosen to gauge AU equals 0.
Yeah, I'm wondering if it's easier to, I'm wondering if it's,
AR.
yeah, I'm wondering if it's easier to work out what you're saying in the using the dual gauge field and the dual field strength.
Yeah, that,
Then it's completely exactly dual. So, but maybe you're not.
okay. Well, no, that would be really interesting
Yes.
if that's what it is.
Uh-huh. Yeah, I think there's a lot to be understood about what these divergent, both the divergent electric and magnetic large gauge symmetries actually correspond to in physical theory. Yeah, I think that understanding is still a bit lacking.
Marcus?
I'll ask later. I'll ask also.
Okay. Alright, so let's answer again.
Thank you.
So can I just ask, where do you feel this kind of thing is going? I mean, you know, because if I were cynical, I could say, well, okay, congratulations, you reformulated a true-level soft theorem in some
Yes,
weird operator language.
Uh-huh.
But is the hope that maybe now you can, understand more general soft theorems from this point of view, or what do you think could be the use of this or the next step?
Yeah, so I think ultimately what we kind of want to do is use all of this to really understand, like fundamentally, what's the infrared structure, what's the vacuum structure of both of gauge theories in general, both abelian and non-abelian, because ultimately, all of this is sort of related to this assumption that
What do you mean by the vacuum structure? We're not talking about like confinement in QCD.
No.
You mean even in QED, there's something about the vacuum that we don't understand, having to do with these
Yeah,
very soft
because-
modes.
Right, because usually in QE, I mean, for a long time, like we always taken the vacuum of QFT to be unique. But it seems that what this analysis is telling us is in fact the vacuum structure is not unique, and there's an infinite degeneracy in the vacuum structure of these QFTs. The infinite divergences that we are all familiar with, that these are essentially telling us when these asymptotic, these word identities are essentially are violated. The fact that we have an infinite divergence showing up in a scattering matrix amplitude is simply saying that we're trying to impose